Hello students, welcome to Bencosit. Today we're going to learn about electrostatics. So electrostatics. Now that electrostatics contains two words, electro and statics. Now electro means here charged particles. That means electrons, and statics means they are at rest. So electrostatics deals with those type of things where the charged particles are at rest. Now the question is why we are going to learn about this subject. Now why we are not considering the charged particles to be in a moving condition. So when there is a moving charged particle, it generates magnetic field, and that's totally different kind of phenomena. And to observe that, to study that things, I mean the current and all, first we need to understand what is electricity. So that is the reason where we are interested to learn about the electrostatics. So first we will learn that what will happen if the charged particles are not moving, that means they are at rest. Then we'll learn when the charged particles are in a moving condition. So what's the basic fundamental thing? Electrostatics starts with Gauss law. Now, in the year of 1785, there is a law developed, and that law said if there are two charged particles, one is Q1, another one is Q2, then there is a force of interaction between those two charged particles, and that force of interaction is proportional to Q1 and also proportional to Q2, and that force of interaction is inversely proportional to their distance. If the r is the distance between them, then inversely proportional to 1 by r square. So as a whole, we can write F equal to K prime Q1 Q2 by r square. So here K is the proportional constant. Now the value of these proportional constants depends on the medium as well as the choice of our units. So this law is similar with the laws of gravitation, where we can see that if there are 2 point mass, first one is m1 and another one is m2, then force of interaction between them is proportional to 1 by r square. And if r is the distance between that two point mass, then force of interaction F equal to G m1 m2 by r square. Here G is universal gravitational constant, but here K is not universal constant because here K depends on, that means K prime depends on the medium, but here G does not depend on the medium, but here K prime depends on the medium, but here G depends on the choice of our units. Here also K prime depends on the choice of unit. In case of CGS, the value of K prime equal to 1, and in case of SI, we write K prime to be 1 by 4 pi epsilon. That is 9 into 10 to the power 9 unit. Now here epsilon naught, we are writing epsilon naught because here we have taken that the medium to be free space. If the medium is not free space, then we should have write K prime equal to 1 by 4 pi simply epsilon naught. So, and obviously unit. Now, as we know that the choice of our unit is important, so that is the reason in case of CGS the value of K prime is 1, but in case of SI this is equal to 1 by 4 pi epsilon 0, and its value is actually 9 into 10 to the 9. Now we will try to find out the dimension and the inter epsilon. So in order to find out the dimension, we take the dimension of F and the dimension of epsilon as 4 pi, and 4 and pi are dimensionless quantity. I'm not considering the dimension, so here simply the dimension of epsilon and dimension of q by dimension of length square. So r is the distance, so L represents the dimension. So now we do not know the value of the dimension. What should be the dimension of q? So in order to understand what should be the dimension of q, we will take I to be current and q to be charge. Then current equal to charge by time. So dimension of q should be I t. So we'll put dimension of f to be m l t to the power minus 2 equal to 1 by epsilon, and dimension of q to be I t square L square. So dimension of epsilon equal to dimension of I by t square m l t to the power minus 2 by L square. So that is how we can actually find out the dimension of epsilon. Now we'll learn about quantization of charge and conservation of charge. Now what does the quantization of charge means and what does the conservation of charge means? Now quantization of any physical quantity means there is some least amount of quantity below which we cannot go. So anything is electrified means there is some disbalance in the number of photons to the number of electrons. If there is some excess number of electrons, then this is negatively charged, and if there is some less amount of electrons, then this is positively charged. Now something is electrified due to some for transition of electrons. If some number of electrons is being taken out, then this is positively charged, and if there is some extra amount of electron is there, suppose n number of electrons is there, extra n of number of electrons is there, then this is negatively charged. So no matter if there is some extra amount of electron or if there is some less amount of electron, but the reason of electrification is electron and not the protons, because protons are in the nucleus and they cannot move actually. So that is the reason. Now if the substance to be electrified, that means there is some charge q, the reason of this substance to be being charged is actually this n number of electrons. So that is the reason that n should be an integer and it cannot be any other fractional number. So that is the reason we call these things to be quantization of charge. So no matter what the amount of charge is, but the charge should be always integral multiple of one electronic charge. So that is the statement of quantization of charge. Now, although quantization of charge says that the electrification should be integral multiple of the electronic charge, but the amount of electronic charge is actually very less. I mean, is of the order of 10 to the minus 19 coulomb. So that is the reason we usually do not consider the charge to be quantized one. We generally consider the charge to be continuous one, and later on we'll study the what will happen if we take the continuous charge distribution and we'll calculate the line charge distribution, surface charge distribution, and the volume charge distribution. But for this time being, we're just discussing that the charge particles are quantized. Now we'll learn the conservation of charge. Now, what does the conservation of charge means? Conservation of charge means if there is a system, physical system, and that physical system have some amount of charge Q, no matter it is positive or negative, but the total amount of charge in that system is always constant. We cannot destroy the charge by any kind of physical or chemical or nuclear change or nuclear reaction, or any kind of physical or chemical or nuclear reaction. We cannot create or destroy the amount of charge in that inside the system. So that is what the conservation of charge, electric charge, says. Now we'll try to compare the gravitational force of attraction, the gravitational interaction, with the Coulomb's interaction. So here we are considering the Coulomb's interaction, that is 1 by 4 pi epsilon 0 Q1 Q2 by R square, and here F equal to G M1 M2 by R square. So first comparison, strength. The strength of the, that is the most beautiful thing, is that there are four kinds of interactions in this universe. That is electrostatic interaction, and gravitational interaction, strong interaction, weak interaction. So out of these four interactions, the electrostatic interaction follows inverse square law. The gravitational interaction follows inverse square law, but strong interaction and weak interaction doesn't follow inverse square law. So that is the difference between these two laws with strong and weak interaction. Now the value of G and value of M. Now if we try to consider the charge Q and mass, these are the property of any kind of particle. If there is a particle, it must have any charge, some amount of charge. Maybe it is 0, but it must, there should be charge of the substance, and it must have some mass. Now if there is a particle, it must have a positive, negative, or 0 charge, and in case of mass, the concept of negative mass is not there, so it must have a positive value of mass, but Q may be positive or negative. That is the reason this kind of force is only attractive, but this force may be attractive or repulsive. If there are like charges, they will repel each other. If there are unlike charges, they will attract each other. But here the interaction is only attractive, it's not repulsive in nature. Now if we try to learn about constant, here the value of K is actually constant, but here the value of M is not actually a constant quantity, because in case of if we learn special theoretical relativity, you get to know that M equal to dou of M0 1 minus V square by C square. So if the value of the velocity of the particle is comparable, here V is the velocity of the particle and C is the velocity of light. So if the velocity of the particle is comparable with the velocity of light, then the value of the mass increases. So here the mass is actually medium, so here the mass is actually velocity dependent, but here the value of Q is not relativistic quantity, so the value of Q is not mass dependent, but velocity dependent, but the mass is actually velocity dependent. So that is why what we actually say that the mass is actually velocity dependent quantity, that means relativistic quantity, but charge is not a relativistic quantity. Next we'll learn about the electric field and electric lines of force and continuous and discrete charge distribution.